Good evening. Just before I start with the actual proceedings, I just want to mention to anyone who's new to this lecture theatre that if we do have the unfortunate occurrence of an alarm, then you can not only go out through this door, but also you can go down the stairs very carefully there. My name is Clive Williams. For those of you who don't know, I'm Dean of the Faculty of Engineering, Mathematics and Science, and it's my pleasure tonight to be introducing Professor Stefano Sanvito. And we're gathered here, both the Provost, colleagues, friends, and indeed family, and you're all welcome to mark the occasion of Professor Sanvito's award of a personal chair in condensed matter theory. The school gave me 4 pages of notes to read out, but that's the bad news. The good news is I'm only going to read out about 4 or 5 sentences. But there's a lot we could say about him, but perhaps we'll let his research speak for that. So Professor Sanvito graduated with his laurea in theoretical physics from the University of Milan, then went on to do his PhD at the University of Lancaster, and once again we have the pleasure tonight to have his PhD supervisor, Professor Lambert, somewhere in the audience. I did see him earlier on. I can't see. The lights are so strong here, it's very difficult to see you. And then after a period in the US, he came here in 2002. And he's had quite a rapid rise in the ranks, well deserved. And of course, he's not done that just by doing research. He's contributed to teaching many undergraduates and postgraduates, and indeed done his fair share of administration, both in developing new teaching courses and indeed being Deputy Director of CRAN, our Nanoscience Institute. Since he's been in TCD, he's established the Computational Spintronics Group, and I'm sure most of you here will know far more about that than me. It's interesting that it says here the group develops and maintains the Smeagol code, which I don't really know what that does, but obviously it has certain literary allusions in the name. And indeed, Professor Sanvito's reputation was recognized last year by the award of a European Research Council Investigator Award, which of course not only recognizes his contributions in his research area, but also allows him the financial support to work further in these areas. That's enough talking from me, if not Tolkien, because I notice that the title of the talk is One Application, One Material, and One Theory to Find Them All. So, Professor Sanvito.
Okay, so welcome from me as well. And so this is something you wait for some long time, and I have to say I'm really freaking out today. In particular because I have to speak in front of a very, very mixed audience. I have colleagues, students, friends, mom and dad, and somehow actually this is, makes the talk more difficult. And I'm very pleased you're all here. In particular, I'm very pleased that a friend of mine who had a very bad accident last year managed to come here. So I want to dedicate the lecture to Joël. The other thing I want to say before we start to discuss what this one application, one material is all about is I want to acknowledge the people that at the end of the day built the chance for me to get this chair. The chair is built of the work of a lot of people. We don't do really anything. We just channel the talent of others. And I pull up a list of everybody has been passed through my group. The blue one are not the more intelligent, the other one are still in the group. And I think you see the list is very long. And I just want to mention that something that at some point I remember a conversation with Viggy McGovern, and we were discussing about an extremely talented student. I don't know if you remember that. And you told me, I was actually celebrating how good was this student, and Iggy told me, you know, you did a very bad mistake. You shouldn't work with these people. I said, why? Because actually working, you never have to work with somebody who is much more intelligent than yourself. And I think actually, when I see the list, I find out that actually I did this mistake many, many times. So I think I want to really thank all you guys for the work you put here. Then there is a number of friends and colleagues that has worked with me for many, many years. Again, a lot of you have been very, very important to do what we do. And in fact, I think is actually because of these collaborations that actually the work can really thrive. And then last but not least, I think I will move to this pointer. I want to thank all these people because essentially these are all the founding agencies that at various time provide the funding to do what we do. So ultimately, in this actually is a lot of Irish taxpayers, so it's you again. Okay, so that essentially just to thank everybody, so I wouldn't forget at the end. Now let me try to kick off with a lecture. So the issue is one application, one material. Let me discuss this part first. So I want to do it by showing you a movie, which are blindly downloaded from YouTube. So look what this guy does. So this was on the Discovery Channel at some point. Okay. Now, just actually to give you a little bit of disturbing news, that mat is roughly the size of my neck and has roughly the density of human flesh. Okay. So what this guy is doing can happen to each one of you or me, and it's not very nice. Now, what this guy was actually doing was handling a katana sword that many of you might have seen in various movies. Now, this actually is a technology that actually started in the 12th century and was by miles the leading technology in cutting weapons, and actually was essentially the leading technology in cutting weapons for the following 800 years. The Japanese never stopped to produce this even after World War II, in fact. Now, this is a particularly good one. In fact, it's the top notch of the katana swords, and there is a big collection in the Tokyo National Museum. Now, why actually this was the leading technology for 900 years or so? In fact, probably still is. Essentially was due to the fact that the Japanese could manipulate these two materials, carbon and iron, making an alloy, and actually not just making an alloy, but making an alloy that was specifically custom-made for that particular application, which is the katana sword. In fact, actually, the way you have to do it is the following. Iron, when you dissolve carbon into iron, become harder and harder. You can actually do too much, but actually more carbon you can put in, harder it becomes. And when steel is very hard, you can cut it very sharp, but it's very brittle, so it can break. However, when steel is less hard, is much more resistant to fracture, but cannot be sharpened up, and your sword actually is not going to cut after a while. So actually what this Japanese craftsman managed to do was to essentially compose a sword. So this is a cross-section of a sword, combining hard steel and soft steel in a very, very specific way. Now, the ways that we're doing essentially was through a very, very complex process of heating up and cooling down iron. And this was essentially, please, no. And this, I really want to put this graph, but just actually for the moment, for the people who are not technical background, forget about for a second. The rule of the game is the following. If you heat up steel at about 1,000 degrees, you can actually dissolve a significant fraction of carbon in iron, so up to about 0.7%. Now, then actually what you do, if you cool it down slowly, you ended up in this type of steel, in which you have grain of different materials with different carbon content, and this is soft. If you cool it down very quickly, you ended up in this one, which is called the martensite phase, and this is actually very hard. So the same material cooling down slowly was giving soft steel, cooling down fast was giving hard steel. And actually, this craftsman, of course, didn't know anything about that. Didn't know anything about this phase diagram. Didn't know anything about all the metallurgy at the atomic level. But they knew that they have a recipe to produce the best swords. And this actually holding on for 900 years. So I think actually the take-home message from the sword story is that the success of this leading technology, and you can call it that, was the ability to manipulate one material. and to exactly transform this material in what was most useful for the application. So it was one material, one application. Let me give you a second example, which is a little bit more close to us. So it's the computer industry. Okay? This is actually was the very first computer, at least of a modern age, that I know. It's called Colossus. This was used by the British to essentially partially find out the code for the German transmission, the transmission of a German order to the troops. And this actually was as large as probably this room also. It was not very fast, but actually it served a purpose. By the end of the war, there were 10 of them, and actually they were absolutely important to find out, particularly the track of submarines actually around the coast of the UK. Now, let me just show you a little bit of history of, but this actually, of course, was not a general purpose. This computer actually did only one thing. It was try to find out what the German were transmitting. So let me try actually to find out, to look actually what is the story of general purpose computer. So this is one of the first one I could track. It was called the Intertek Superbrain, and was produced in 1979, sold. It didn't have an hard disk, but you could upload things with a floppy. And it cost $2,000 for 4 megahertz of speed. Now, price actually doesn't mean much. So $2,000 at the time, the average house in the United States, new house, was about $60,000. So it was a significant purchase. A lot of you remember this. This is the very, very famous Macintosh. Speed went up almost twice. Now you have an hard disk. The floppy has also changed. $2,000 against the house price of $8,000. So price was coming down a little bit. Funny enough, they all cost $2,000, although the number is always 2,000, but the price of the rest changes. There must be something magic with this 2,000, actually. IBM PS1, 1992, same story, big, big success. IBM actually produced about 10 years worth of those computers. 20 megahertz, $2,000, against 120. This was one of my favorite one. And then let me go to probably one of the most iconic of the recent time, the Air Mac, Mac Air, 1,000, that came down in price. And now you buy an average house in the US for $250,000 or so. Now, what actually means, what you see here, you see an enormous progression in speed and capability of a computer at a cost which is coming down, okay? Now, if you think about any other applications that require high tech, you will see the same story. I give you the mobile phone here, the Nokia. This was called the Brick for obvious reason. Same story. It cost a fortune. The battery of this guy will last for about 10 minutes. And now you have this super smart one. Now, the issue is, this is actually how all this high-tech technology works. You know that tomorrow somebody is going to persuade you to go to a shop, buy a new mobile phone, and you know that this is going to be twice as fast, twice as powerful, twice as smart, twice as whatever than the one you have before. Still, it will make the same phone call, of course, but it's going to have all this other feature. Now, why is this? This is the reason actually was forecast by this gentleman here, fishing somewhere, by the name of Gordon Moore, who essentially said that, predicted at some point that the speed, essentially the number of transistors in a computer would double every 2 years. If you factor in that when the amount of transistors double, also other things improve, this ended up with the fact that the performance of the computer doubled every 18 months. And this actually was not just a prediction, then the semiconductor and computer industry decided that this was the way to go. It's also something to do with maximize the price of selling electronic equipment. But anyway, this actually happened. And this is actually a plot of a Moore's law. So this is the number of transistors you have in your computer as a function of time. And you see that the superbrain was roughly here. So it has about 5,000 transistors, 50,000 transistors. And now when you buy one of those guys, you have 2.5 billion of transistors. The size didn't get any bigger, okay? So the beauty of this is somehow we managed to squeeze a transistor in a computer at a rate that in 1980 you have as many transistors as the population of Limerick, and in 2001 you have as many population of China and in India combined. Okay, so that's spectacular. And if you think about any other technology, this has no precedent whatsoever. So let's suppose I want to do this with cars. Okay, in 1908 you could buy the 4T. By the way, this was $800. And was actually, the top speed was roughly the one of a horse, 50 kilometers an hour or so. If you assume the car industry would evolve with the Moore's law, and I give you a discount, I give you a Moore's law cut by 2, so only a doubling every 4 years, now your car would go at 1.7 billion kilometers per hour, which is actually roughly 1.5 times the speed of light. Okay? And if you do another interesting one, you try to find out what is the petrol consumption, you will find out it will do 200 million kilometers with a liter. So a drop will last for quite some time. So of course, there's a physical limitation. You can compare the two. Of course, the speed of light somehow set a limit. But anyway, the car problem is very different from the computer one. But it's actually just to give you a feeling of how extraordinary actually was the development of the computer industry. And actually, I really like this. Let me give you just a disturbing fact. This is actually a plot of the number of calculations that you can do per second per $1,000 as a function of time. And this is actually what the computer did. And finally, here actually you see what actually living being can do. And what you find out, probably very disturbing, is that actually by 2020, which is not actually terribly far away, a $1,000 computer can do the same operations that a human being. So actually your computer is going to be as intelligent as you. Now, fortunately, intelligence has nothing to do with ability to process a lot of information, yet I found actually a rather disturbing fact. Now, why this was possible? Because actually, people in Intel and any other semiconductor industry managed to reduce the size of a transistor, which is the key element in your computer, in a spectacular way. So this is actually a very out-to-date roadmap from Intel, and you see that actually more or less we're here now, and a transistor now is about 20 nanometer long. Now, 1 nanometer is 1 billionth of a meter. So if you take me, you cut me in a billion slices, one slice is going to be 1 nanometer. So actually, this is small. This is very small. So for the computer industry also, the ability to manipulate a material actually said it all. So the ability to manipulate a material is what defines, without any shadow of a doubt, a technology. So one application, one material again. Let me actually just give you a feeling of why silicon. Why actually could have you done this with any other material? Well, the first reason actually silicon is a semiconductor, so you need one of those to make a transistor to start with. But actually nature has an enormous amount of semiconductor of all sort of kind of shape, picked up from all region of the periodic table. This is more or less a random selection of them. Then you can say one characteristic is electrons, which is the essentially is what the carrier of electrical current, have to move faster, because if you want your transistor to be fast, electrons need to be fast. So a way to measure it is the mobility, which is roughly is the velocity that an electron would have if you apply an electric field of a certain magnitude. And so this is the number for silicon. And, well, the number cannot say much to you. But actually, if I put in comparison with other material, you find out that actually silicon looks pretty lousy at the end of the day. So germanium, which is just one down in the periodic table, does actually twice as better. Indium antimonide, which is actually an interesting one, does almost 100 times, 100,000 times better. So I mean, why you pick up silicon? Originally, you need an oxide, because when you have to create a transistor, you need an oxide. And silicon is a very good one. You just need to flash some oxygen on silicon, and silicon becomes silicon dioxide. But a lot of other material has very, very similar insulators that can go with them very well. Gallium arsenide, aluminum arsenide is a very good example. And anyway, this requirement is not any longer valid, because now people don't use silicon dioxide anymore, but they use something else that is grown on top. So this also doesn't seem like a good reason. The price. OK, here silicon doesn't do too bad. So $2 per kilo. If you want to do the same with indium antimonide, it's $500 per kilo, so your computer is going to be 500 times more expensive. It's not good. But organic objects are typically cheaper. They can be processed cheaply and so on. So price is not the unique reason. You have 70 years of knowledge. So people have been handling silicon for the last 70 years. So there is a lot of accumulated knowledge in handle this material, and there is an enormous amount of investment. In Ireland, Intel invested about 10 billion in the last 20 years or so, and probably is a conservative estimate, actually. I couldn't find anything terribly new here. So my point is, why silicon? Because of all this reason. So actually, silicon is the only material that ticks pretty much all the boxes. It's not the best in any one of those, but actually it has all of them. So when you have a modern technology, a material has to have an enormous amount of requirements. And this enormous amount of requirements has all to be met at the same time. So let's suppose now you have a new beautiful technology of some kind, and you're not happy with the material you have, or you don't know actually what is the best material. How will you go about it? So the idea is how you discover new materials that are custom-made for the particular technology and for which you either don't know where to pick in the existing one, or actually you need to create a new one. Now, this is an enormous challenge. And in fact, usually the US are quicker to pick up these challenges. Obama in 2011 gave a for us, very interesting speech in Carnegie Mellon, where essentially launched what is called the Materials Genome Initiative for Advanced Manufacturing Partnership, where essentially the aim was, let's find collectively a strategy to develop materials very, very quickly, very, very efficiently, and very, very tie in with particular application. So let me try actually to explain you how you can develop a concept of finding new materials for new applications and where actually you don't have a guiding map. So let me try to entertain you a little bit with this material genome concept, which in my opinion is the most exciting thing that has appeared in computational material science in the last number of years, in fact. So what theory usually do? As you heard, my chair is about theory, so we do theory. So usually theory interprets experiment. So a colleague of you does an experiment. This, I think, was stolen from one of Maiko's paper. And you recognize this one? And essentially, then usually the interpretation of the experiment might not be transparent. And then usually you come to a theoretician. Theoretician try to make a model of the experiment, try to find out what went right, what went wrong, how to improve it, and so on. Now, the key challenge is, can we do the opposite? So can we first start from the theory and have a theory designing the new material for the application you want to make, and starting from the white canvas and try to fill it up? So what is the idea? The idea actually borrows heavily from another completely unrelated subject, which is the subject actually of the genomic. And so let me try to give you the spirit of this. You know that there is a lot of activity now in trying to code, and in fact was successful, the entire human genome. So essentially the idea is each one of us has DNA in every single cell, and DNA actually is the code of how essentially our human body is going to evolve. So it contains information about how you synthesize proteins, so information about how you're going to have blue eyes, blonde hair, no hair. But also actually it's very important because actually it contains information about how likely you are going to be to develop a disease, for instance. So it's very important to know this information, and it's very important to actually to be able to construct an enormous amount of database where actually all this information are contained. Why? Because then we can cross-check with the life of people. We can find out whether a specific part of your genome give you likelihood to have a specific disease, and then you can act. So you find out that actually you're likely to develop, say, diabetes. You probably wanted donuts for breakfast. And this thing actually can help to improve the quality of life. Furthermore, you can design therapeutics that actually are custom designed for yourself. So this is an enormous area of an enormous importance. But the concept I want to stress is the following. Taking reality, constructing database that interpret the reality, and then actually face the reality again and find out actually how you can extract information. So can we do this for the search of new materials? Well, I guess the answer should be yes. Now, we have as well our DNA. On the planet, nature has provided us with a lot of materials that we know. This is gold, this is carbon again. This, I think, is carbon again, and this is iron. So, and then, in principle, we can construct databases of materials. So we can categorize these databases, have all the property written in, and actually have a gigantic list of what are these materials. And actually, we can find out how this database of property related to property that are connected to devices. So maybe we can find out that for a particular device, a particular class of material is good. But the issue is, if the material you want does not exist yet. By the way, every year, about 100 new inorganic materials are discovered on the planet. So actually, the room for new materials actually is quite large. So how actually you do? And this is actually where theory can help. So what we can do, actually, we can act here and provide a second level of reality, which is not the reality of the real world. It's not the material you can find in a mine, but the material you can simulate on a computer. And we can create this enormous database of material, existing and hypothetical. So we use computer to interpret our materials world and to try to find out how the property of the material at the most macroscopic level are explained through the theory. So we can now start to construct a gigantic database where not just the existing material, but the new one that not exists yet can be included. And then, because we have an enormous amount of information, then we can try to understand, one, how the rules of nature goes, two, how actually we can pick up the best material for the best application. And of course, finally, we should act. So we should go to one of our experimentalist colleagues and actually ask them to make those materials. This is the difficult one. So what are the steps required to do this sort of simulation of nature at a massive scale? So first of all, actually, we need what I call the virtual material of growth. So actually, we have to simulate in a computer every material can be possibly made. Every most wild dream you have about material need to be simulated. And of course, we have to simulate all the existing one, because we need to be sure that we're able to predict whether something we simulate would eventually exist. So this is the first step. And the way we do it, you need a robust electronic structural methods. Now, this is just a word, you can forget it in a second. It's called density functional theory. This is probably the most accurate way to simulate the materials world at the macroscopic level. So actually take into account real atoms was worth of a 1998 Nobel Prize in chemistry, in fact. Then actually you have to be able to take this material and put in a database which is accessible, searchable, and useful. And the way to do it, actually, here we have a code. I'm going to get in a second to that. Will actually create this database automatically. Now, when the flux of information is enormous, you can't just do by hand. You can actually, for every material, start to create your web page. This needs to be done automatically somehow. And finally, and this is really the difficult one, we have to find out how to speak with this database. So we have to find out a language with which actually we ask to the database what are the key parameters of the material for the specific application, and try to pull it off these materials for further screening. So this is called we just wrote a paper which is going to appear in Nature Material in a week's time. It's called the High Throughput Highway to Computational Material Design. And essentially to do this, this is a big project. We form a consortium, which actually is here in few places in the US and in Israel. And with all people with different expertise, going from material science to, say, database and artificial intelligence skills. And we try actually to see whether this can be put all together. So let me try to go one step at a time. Let me show you the first virtual material growth. So how many material can you really possibly make? Okay? So at the end of the day, you have the feeling that if you start to count how many material you know, that not that many. So it's the periodic table plus a bunch of few others. Okay? Now, if you think about it, actually, there are quite a lot. Now, there are 14 possible ways to fill up space in 3 dimensions by repeating units. This actually 14 possible ways can be obtained by putting in each one of these boxes atoms arranged in a different position. And this actually is very, very entertaining and funny, This is actually strontium titanate. It's an insulator that is used for some optoelectronic application. This is actually polonium, which is actually used to kill a Russian spy in London. It's a very radioactive and poisoning material. And those two actually are all coming from these structures. So the same structures can produce spectacularly different material depending on how you fit the atoms in. And actually, you have 14 of those. Plus, you can pick up materials from the entire periodic table. Some of them won't work, of course, but actually you have a very, very large number. So it's very difficult to estimate how many you can possibly make, particularly because some of them are probably spectacularly bad ideas that will never be made, so nobody will ever think about doing it. So for instance, you can put too many atoms in the same place and all sort of simple rules. But I would say there are probably several millions of those you can make. Now, how many we know about it? 150,000. So this essentially, and 100 a day are discovered. So this essentially means that I'm sure there are out there a lot of new materials that actually are just waiting for somebody to find them out. Sometimes actually material are not discovered simply because nobody looked for them, because it's not interesting at the time. Because actually sometimes there are a lot of examples where you're looking for a material and you find another one, in fact. And so there's a lot of actually reason why you don't have a lot of materials. But actually not that many. You can read this. This is essentially all this material of the somehow catalogized in this database, which is probably one of the most reliable. And this is actually what is inside. So actually what we need first to do is to take all this material and calculate the electronic property of those materials. So actually try to understand how those materials that exist and why they have the properties they have. So we start to do that, and this is in fact was carried on by our collaborator in Duke in the US. And essentially we have about 20,000 of them, because essentially what we calculate what is useful for that specific problem. We don't just go blind till we do the full 150,000. Some of them come up quite badly with the method we have, so we have to stay away from them. Everything actually contains oxygen. It creates a lot of problems to us, so you have to be a little bit careful. But nevertheless, this is what you do. So then actually, so we have this database of the ones that exist. So point number 2 is we have to store those in a very convenient fashion. So we have to do this rational material storage. So we have to categorize that. And here actually I'm taking a very bold step. I'll try to do a live demonstration of how this is done. So it usually doesn't work even for Bill Gates, so I think I'm okay. So we created this database. And this database actually, once the calculation is done, the calculation enters in the database and automatically. And there is a search portal where you can access. So what you can do actually, you can type whatever the characteristic of the material you're looking for. So you can ask, you can look for materials that contain a specific element, that have particular lattice structures. If there are semiconductors, they might have band gap, and so on. And then actually you press the button and you see actually what exists. So let me actually do an example. You want to propose an element of a periodic table? Pick a simple one. Let's go to the transition metal, because this is actually for, this is intermetallic with transition metal. So let's say iron. Another one. So what did you say? Platinum. Platinum, we have it, yeah. Another one. Let me say manganese, okay? So this is going to be very embarrassing now. Oh, here we go. Okay. So, and this actually, all the material has been calculated according to this specific rule for the database I'm going to discuss in a second. And here you have a plot of all the possible information. This is all done automatically, okay? Of the possible information you can think about a material. And let's suppose that, okay, by the way, these are ordered in alphabetic order because you have to have some rule actually how to construct these databases. Let's suppose for some reason I'm interested in this one. So it takes a while, and then you go to another page, maybe, okay, where I knew this has to happen. you go to another page where you actually read all the information of the calculations. You can score with a reality if the material exists. So you know actually what this sort of a... oh, OK, why this is out of the screen? So you can also see how this look like. So this look like this. The purple is manganese, the iron is orange, and the white is platinum. And then actually you can also see what are the electronic properties. So this is more for expert. You can see band structure, density of state, and all these kind of things. You can also see a funny number here. It's called formation energy. And this is actually tell you if this number is positive, the material certainly is not going to exist. If the material is negative, it has some chance. This actually looks negative, but very small, so I think this probably does not exist, in fact. So this is actually how you do. So you can construct this database, which is searchable. In the near future, people, at the moment it's a little bit private, but in the near future, the idea would be to make this public. So by the way, I have to kill you all because you saw this. OK, now, and actually the last part is now we have a material. Now actually now we have a database, all this material in the database. We know the existing material. We know the rules. We decoded everything. Let's pull it off the useful one. OK? So, and this is actually the part that is mostly carried out in Dublin. In fact, we named this part of the project the Magnetic Genome Project. Now, why actually pick up magnetism? OK, first of all, because this is something I've been working for a very long time, and it's something I know well. But also because magnetism is one of the very examples where changing tiny details change massively the property of a material. So actually, sometimes defy completely intuition. And I want to give you this example, which I found really amusing, actually. So if you take this crystal, which is the perovskite, and you take one particular way you can form this crystal, where strontium fill the yellow balls, oxygen the white one, and another material that you pick up in this region of the periodic table fill the black one, then you have a transition metaperovskite, and you have magnetism. And actually, look what happened. If the black atom is chromium, you get a magnet, which is magnetic at minus 230 degrees. So actually, it's magnetic probably only on Jupiter or, I don't know, Pluto, one of the cold planets. If you take manganese, you have strontium manganite, and this is also a magnet, but at minus 10 degrees. So this is not too bad. It's magnet in the winter. It doesn't become magnetic in the summer. Then you have strontium ferrite, also quite bad, minus 100 and so. Strontium molybdenite never made magnetic at all. So you can cool it down as much as you like. Nothing ever is going to happen. Strontium ruthenate, magnetic, but at minus 100 degrees, so not very useful either. And, well, why I left one in the middle? Well, because in the middle I've got technetium, which is extremely radioactive. So nobody actually sane would ever think about doing it. Now, for some reason, actually, someone in the UK a couple of years ago did it. And, I mean, what you would really expect, you're surrounded by a collection of extremely lousy magnets. You're going around the periodic table, you find nothing. And then you take this strontium technetium, is a magnet at 500 centigrade. So this actually is amazing. And, well, the reason for that actually is a very subtle competition between having relatively large d orbitals and a very large distortion of the octahedral cage. But nevertheless, the point here I want to make is magnetism really defy intuition. Okay? So then, essentially, unless somebody would have grown this material or somebody would have done the calculation, there was no chance for you to understand that actually, to guess that the material was magnetic, at least for me. And actually, just to actually give you a feeling how spectacular this is actually a chart that Mike actually put together some years ago. So this is an histogram of magnetic material ordered by their ordered in temperature. Now, I'm sorry, here I moved to the Kelvin scale, but so strontium technetium is here. And actually, as you see, there are very, very few that actually can beat him up. And because this is a very difficult and rare event to find a new magnet which is useful. So a new magnet which has a high critical temperature. So how do we discover this? Well, we have to do calculations. So we have to, but we cannot just take all the possible 2, 3, 10 million material you can make and try to make them all. So we have to take a rule. And the rule actually for us is to take a particular lattice structure, which is called the oscillator lattice structures, because actually this is a family of materials which has a lot of magnets in them. And this essentially, the crystal look like this. There are three different types. I don't really want to go in the details, but and essentially what you see is you can pick the red atom from the red in the periodic table, the green one from the green, and the blue from the blue. And essentially what we said is only 150 exist. If you look in the literature, actually people quote about 1,050, but actually when you go to see carefully, a lot of them are repetition or tiny modification of those that exist. So the real unique one at about 150. Now, if you try to find out how many you can make, you come up with several 100,000. And so what we did is like, let's do all of them, okay? So we start to do the calculation, and then this is one of the output of the calculation, and you calculate one. So this is a bizarre one. Then you calculate one, and essentially you start to crunch the machine. You don't do things, it's the machine doing it. So you piss off a lot of people around the world because you use their computer, but then eventually you do it, and then we done all of them, okay? And these actually are 235,253. And so these are all of them. So this actually, if any material with this crystal structure can be made, is going to be there, okay? Now we have to find out whether or not there are some useful and whether or not there are well, they exist, in fact. So we have really to find out this, to interrogate the database. And this is the tricky part, because actually this is where you need to find out what is the language of nature, which is always the tricky part. So I give you two quick examples. The first one is to find useful material for the data storage industry. Now, each one of you has an hard disk somewhere. An hard disk is essentially a magnetic disk which is read by this object here. If I zoom in this object here, you see these things. So this actually is a piece of material where current passes through, okay? But not just current. There is actually a particular property of the electrons, which are the carrier of the currents that you use, and it's called the spin. So you have to think about the electron carrier as charged particles that either spin clockwise or anti-clockwise like a little planet. And actually, the property of magnetism are determined whether or not the spin is clockwise or anti-clockwise. Now, the current in a normal material is carried equally by electrons that spin clockwise and by electrons that spin anti-clockwise. In magnet, this is no longer true. Only one of the two species, one of the two species is dominating against the other one. And the best way to obtain extremely sensitive read heads is to have material where actually only one spin is present. These are called half metallic material. So we have to look for those. Now the question is, now we have to find a language to explain to our calculated database how I describe this property. And this language is the density of state. Now, again, I don't really want to get in any technicality here. The only thing I want to mention is the density of state somehow is tell you how many electrons you have at a particular energy. And in particular, the density of state at the Fermi level tell you how many electrons you have that are responsible for the current. So what you have to look is density of state for material where only one spin has a density of state and the other one has no density of state. So you define a mathematical expression, which is here, which is called the polarization. And actually, this tells you whether or not a material is going to be an half metal. And this is the language that the computed nature speak. So we run this through the database, and we find out that among the 235,000, 5,000 of them are half metal. And then you say, wow, that's pretty good. You told me that it's very difficult to find one, you find 5,000. Now, then actually you have to ask yourself, well, but can this really be made? Okay, it's good to find new materials, but do they exist? Now, how you do it? Well, you have to find out whether the energy to make this material is less than the energy of its parts. So actually, you have to calculate whether the energy of a composite is less than the energy of the three guys together. Otherwise, the material will not form. If you do this sanity check, you find out that among the all possible, only 57,000 have some chance to be made. But among the half metal, only 1,400 can be made. So actually, if you want a material that is likely to be made and has this particular property, now you have only 1,000 or so of them. So actually the search becomes tricky. But this is not the end, because actually once you find out that the energy of your new material is less than the energy of its part, you have to ask, are these the only parts that can be made? And the answer, unfortunately, is no. So if you start to look in the other database of the existing material, for instance, for this particular one, nickel, manganese, aluminum, you will find out actually that manganese aluminum can be made, and actually has been made for a long time. And this means that the material can also break in nickel plus this alloy. And then you have to check that now your material can be made against those two. Now, if we still make it, so the energy is still here, you have actually to look for more. So you have another two to look at, and you have another composition that actually can be competitive. And then you have to check all of them. And this, of course, becomes painful, because actually, in fact, you don't need just to check for the ones that do exist, but for the one that actually you have in your database. Because actually, it might be that the material you're looking for that does not exist is actually competing with another material that does not exist yet. So actually, you have to do all of them. And OK, we have a lot of very complicated rules to essentially find out what need to be calculated and why. And if you do everything, it takes really a lot of time, a lot of pain, and a lot of computers. You find out that actually it's possible to make prediction. So this nickel, aluminum, nickel to manganese alloy is found stable. Three other of the same family are found out not to be stable, are all stable against fragmenting in the pieces, but are not stable against fragmenting in different compositions, in fact. And actually, we find out that this is also quite interesting one, because it's what is called is potentially actually a shape memory alloy that actually preserve the alpha metallicity. So this is actually a very interesting one. However, actually, these calculations are very painful. And for instance, you see here that we have 4 candidates to start. Only one, when you go through this scrutiny, actually is going to form, which essentially means that likely over this 300 and whatever thousand, you probably are going to have 10, 15 of them, which are useful and can be made. So sad story, but is certainly much quicker that asks you to synthesize all the 300,000. So this is very much ongoing. We're doing a lot of screening now for all sorts of reasons, and I think we are finding a lot of interesting things. Now, very quickly, let me give you another one, because now here I want to show you a twist of the story. So how actually constructing this database can help us not to find new material, to understand new laws of physics, or at least to understand why some particular material behave as they do. Now, this is really coming up from another application. So if you want a very hard magnet, which is a magnet that actually, a very hard magnet, let me give you a very scientific definition. It's a magnet that sticks extremely strongly of your fridge, okay? Now, you need actually to have those for a lot of application. One for all is energy production in electrical motors and turbines and so on. Typically, materials that actually have this particular lattice structures do not behave as a very strong magnets, because actually for the particular reason, because actually the atoms are arranged in a cube, and the cube actually, this particular arrangement usually tries to kill what is called the magnetic anisotropy, and therefore the interaction, the magnet actually cannot be too hard. However, if you stretch, this is a PowerPoint stretch, so also the atom got a little bit stretched, but if you stretch the cell, this actually now can sustain very large anisotropy. So actually the argument is like, okay, so we found a rule, which is some sort of an intuitive rule, by which we can calculate the anisotropy. Now, why we do that, we don't just go ahead and calculate the anisotropy, because this is a very painful calculation to do, very heavy, so we don't want to do this right away. And actually very accurate, so it's very easy to get it wrong. But this actually is quite simple. So, so as I said, here we don't want to produce new material, we want to understand why actually material behave the way it does. So the first thing we did was like, let's take all the existing one and find out which one of them actually for some reason make this distortion. And what we find out actually is there are only 13. And this actually is really somehow weird actually. You have 150 you can make, 300,000 you can potentially make, and only 13 really distort for a reason or another. Now, the one listed are more than 13 because actually this blue one has never been made. It's just been calculated by others. So the black one are the one being made, and we found out only 13. So the argument is why actually this is the case. So we went back to the database. We look for materials. We look for this particular property of distortion. We found actually that in the hypothetical structures, many more of them can distort. And actually, we try to look what is the, again, electronic structures that accumulate all of them. Now, if you look at those materials, honestly speaking, I really challenge you to find a commonality. I mean, they come from any sort of region of a periodic table. Some of them are magnetic, some of them are not. I honestly, when we start to look with Tom actually here, we couldn't find out actually a particular reason. But then we went to the database, we looked very carefully, and what we found out is that they all follow this particular reason, this particular story. If you calculate them and you fix the atom in a non-distorted situation, and you impose by brute force that these are not magnetic, you find the density of state almost always looking like this. Now, for those of you who know how to read these things, when the density of state is like this, so you have a big peak at this particular critical energy, which is called the Fermi energy, the material usually will try to spontaneously generate magnetism. So, in fact, almost all of those become magnetic. But now, when you do this, because the density is this peculiar, some of them still end up with a peak at the Fermi level. And then there is another mechanism that can kick in, which is a structural distortion. And the structural distortion then open up a gap. You have to have some other thing actually going right for this to happen, but it's actually what we found in the database. And the structural distortion give you this new density state, which is actually the ones that lower down the energy. So actually what we found by looking in the database is essentially that the emergence of this particular class of material is due to two competing factors that are technically called the Stoner criterion and something is called the band-Young-Teller distortion mechanism. Now, the two are competing. So actually, we are writing down a free energy where you can see that depending on how the material exactly are, you can distort and be magnetic, be only magnetic, or just distort. But I want to put this up because this is a demonstration as you don't need to find a new material. Here we are interrogating the database to find what is the rule that accumulate materials. And now that we know what it is, now we're going to find out whether there are some out there that has not been discovered and can be made. So finally, let me just try to address the issues like, oh, this is all beautiful, but is this useful? Now, I'm personally extremely fascinated by the whole concept. So to me, at the end of the day, what is useful or not is less relevant. But I think as a scientist, you only have to ask what is useful or not. Okay, I think it's actually quite a mandate you have with society to actually make something which is useful. So, so it is useful. Well, I think actually from the contact we have with a lot of people out there, it seems to be the case. So we just have a project together, which is actually is waiting for funding, in fact, with Seagate, and is about designing materials which are custom-made for making this readout for our disk drive. Now, actually, what Seagate want to do is to design not just the magnets, but also other pieces that actually go to form these particular readouts. Now, why actually Seagate want to have a more sensitive readout for our disk drive? Because the demand for storage space of data is growing at a spectacular speed. Now, and again, I want to give you an amazing number. An estimate says that there are about 2.5 billion digital cameras on the planet, including mobile phones. If each one of them snap about 200 pictures a year, makes 1 billion gigabytes of pictures produced worldwide, and 35% of them ended up on Facebook. Okay? So this means that the demand of data storage is enormous. I think IBM estimates that by 2050, you would need a hard disk drive of a diameter that goes from the Earth to the Moon. Okay, so that's serious things. Now, okay, this is another one. Is close to my heart. This is a project which has started. Is a large European collaboration. Now, this is a completely different ballgame. If you want to construct a permanent magnet, which is very hard, particularly for energy application, At the moment, the present technology required to use a particular row of elements in the periodic table, which are called the rare earths. Now, it turned out that the rare earths are produced in the vast, vast majority in China, which is actually not a problem, except that the Chinese make the price. So actually, there is an enormous volatility on the market about the price of the rare earth, and the price actually is nowhere near to correlate with the natural abundance. So actually, are more expensive than other materials that are more rare. So of course, Europe wants to design a strategy, and the US as well, to design new materials. And this is why we get new magnets that do not include the rare earth. And again, in the US alone, US permanent magnet market is about $10 billion a year. So probably Europe is roughly is going to be the same. Now, funny enough, this project is called Romeo, and we have now one which is, we all hope is going to be accepted on the same topic, and by the imaginative mind of Professor Coy, is called Juliet. So we hope we can finally make Romeo and Juliet marry. That's a tough one. Finally, well, by the way it ended, it doesn't look very good. But so let me give you a last one. Now, as a few of you knows, I have this interesting relation with the Arab world. Now, and recently, actually, I was in Saudi Arabia, and we have the discussion with Saudi Aramco, which is actually the guy who are holding the Saudi oil, and they're really intrigued by what we do, and they ask whether we could come up with a proposal. It doesn't mean it's going to be funded, but at least they want to see a proposal to actually solve this problem. In the US alone, $170 billion are spent every year to clean up corrosion from pipes that are connected with oil industry. And pipes break, you have to replace it, you have to stop the production line, you have to clean it up, and so on. So, and this is not just, and this is going to be much worse in the future, simply because oil resources are going to be more rare. You have to dig out oil in very unconventional place, and essentially the chemical composition of different wells around different part of in different parts of the world is going to be extremely different. So actually what Saudi Aramco wants us to do is they want to provide a method to actually custom design alloys that withstand corrosion and are custom designed for a particular geographic region. Now what is very interesting, this is the most secure information they will ever disclose. So actually they will never tell us exactly what is the chemical composition. They just want the methods to address the problem. Now, finally, of course, this is all about computers. At the end, you have to make those materials. So this is why it's very important that this research is embedded in a materials research center, in a nanoscience research center. So everything you have seen here is run, well, most of it is run through CRAN. You need to have this international brief, so there is all this international collaboration around, and this is actually what makes the success. So let me finally, let me conclude here. So I hope what I show you is that the material world is enormous. Very, very little is charted at the moment. So you have this treasure map, and you know little about the treasure map. There is a lot of clouds all over the place, and I hope theory can help you to dissolve a little bit the cloud. So maybe actually we will know where to go. Of course, you have to expect mistake. So when you search for the treasure hunt, you might end up with surprises, beautiful but dangerous. So if we give a material to you and you cannot make it, we might be wrong. But I think actually the reward and the price might be very high. So thank you for your attention. Almost on time.